Good afternoon. This is Joy from Eddie's team at Alibaba Cloud. And today I'm going to talk about our recent efforts on SONiC BGP routes loading time optimization from a software engineer perspective. Since I don't assume that all of my audience are very familiar with SONiC, so let's go over the complete loading workflow quickly before the optimization part. So after the routes are pumped to the Linux kernel, those routes would start from the zebra, and they would follow the direction of the arrows in the picture to FPMSyncD, then to application database, then to Orchagent, then ASIC-DB, then syncd module, then finally to the hardware ASIC. And each pass has its own performance limit, and definitely the slowest pass would decide the overall end-to-end speed. And currently, on Alibaba's platform, the speed is about 10K routes per second, and with the community version around 326. And our target with this project is to optimize the speed to 15K, which is a 50% improvement. And we would continue on optimizing this speed and with even higher future targets. So now let's go to the optimization part. The optimization is majorly divided into two aspects. The first one is about the input and output. We could increase the bandwidth, and we could possibly save much traffic. And second one is to accelerate the submodule processing workflow itself. And let's go to the I/O part. So in community's version, there is only a single Redis server for all the Redis databases. But we have a total of 5. And the application database and ASIC database has its own independent Redis server. The thing is, the Redis server is single-threaded. So if you host all the databases on a single Redis server, they can't work in parallel. And since AppDB and ASIC-DB has their own server, they can work together and they would not affect each other. So this single improvement have large effects. And let's go to the second part. We also optimize how FPMSyncD transmits data to Orchagent via Redis. FPMSyncD, as a data producer, it would wrap the Redis commands into Lua scripts and batch them in a pipeline, and finally flush the data into the application database, which is Redis-based. And the Orchagent, as a consumer, would read the data from the Redis tables. And there is a subpub mechanism here. After the FPMSyncD writes data to the Redis, it needs to publish its changes. So the subscribers would get notified and go to the Redis and fetch the new data from there. And to make sure every new data is detected by the Orchagent, the FPMSyncD would publish every modification. As you can see, inside the Lua script, no matter it is delete or set, there's a publish Redis command following it. And but we made the modification, and we removed the single publish Redis command inside the Lua script and attach a single publish. A Lua script only contains Redis publish inside after the whole pipeline. And that means if we have a pipeline which has a size, for example, 10K, with this modification, we would save 10K Redis commands traffic. And that's a safe part. Now let's go to the submodule part, how to make the modules work faster. And from the picture on the right, you can see what the Orchagent do. All the workload is included in a single API named execute, and I draw it in a yellow block. And the execute can be divided into two sections. The first section is drawn in the blue box, and the second is included in the green box. The first one pops, it's read data from application database. And thread would store the data into its local variable named entries. And the second part, it would transfer the entries into its internal data structure named N2Sync, and finally process the data and process the data into ASIC database. But the bad thing here is after you pop the data from the application database, the workflow needs to wait until the green workflow process the data. And after it processes the data, the blue one can continue to pop new data from the application database. And for the green workflow, it also needs to wait for the blue one to complete its pop, then to handle the new batch of data. And what we want to achieve is that after the first pop, we want to do the second pop and the first green task together. And this is how we do it. We add a new thread named assistant thread. So for the first thread, we just do the simple pops task. And for the second thread, we would do the green tasks. So the benefit here is that after the main thread do the first pops, it doesn't need to wait for the handling. It can directly to pop the second batch of data. And for the assistant thread, after it's process the first batch of data, since the second batch is already popped, it doesn't need to wait, and it can directly begin its processing at the same time, so the whole workflow can be accelerated. But since we have added a new thread, we need to build some infrastructure to support this multi-threading mechanism. And how to do this? Then we propose a ring buffer data structure here. You can see the ring buffer is like an intermediate median between main thread and assistant thread. So after the main thread pops data from the application database, it's no longer need to wait for the green worker to take over the data it pops. It directly pushes the data into the ring buffer and then do the second task. And the green workflow, it doesn't need to fetch data from the blue workflow. It directly fetch data from the ring buffer. So they're kind of decoupled. And the main thread keeps pushing data to the head pointer. And the assistant thread keeps popping data from the tail pointer. Since they deal with different pointers, we can achieve a log-free multi-threading mechanism with the help of the ring buffer data structure. And the ring buffer is itself a FIFO, I mean first in, first out data structure. It's in nature a queue. So the order is maintained. And it's called a ring because when the head or tail pointer reaches the end of the buffer, it would flow to the head of the buffer. And we can even get the status of the ring buffer by comparing the head pointer and tail pointer. I mean, if these two pointers are equal, we can say the buffer must be empty. And if they are close to each other, we know it's full. And when the buffer is full, the main thread has to wait. And until there's an empty slot in the ring buffer, then we can push the new data into the ring buffer. So everything makes sense here. And to support this, we need to add some summary of API design. So the ring buffer structure, it needs to have a head pointer, tail pointer, and a push API and pop API. And the main thread needs to have a push ring buffer API, and assistant thread needs to have a pop ring buffer API because it needs to prepare the data, then store it into the ring, and the assistant needs to pops data from the ring and process. And that's a summary of API. Here's some points. Since we need to guarantee the order is maintained after we adding some new threads, and this order is system-wise. So we need to make sure that we use a single ring buffer. Everyone sees the same ring buffer. Otherwise, it's totally messed up. So we decide to implement the ring buffer with the Singleton. And I think it's a programming language concept. And that's the implementation for ring buffer, you can see we disable the assignment and the copy function. So once you create a ring buffer, it cannot be copied, and it cannot be transferred or assigned. And when you want to access the ring buffer, you can only through this static class function get. And what does this get API do? So at the very beginning, the ring buffer is uninitialized. So when you call the get, the compiler would use new to allocate memory space in heap to give it to the ring buffer. And for the following times, when you query get, since the previous allocated address is stored in the class, every time you query get, you get the same address. So everyone use ring buffer get function to reach the ring buffer. And no matter how many times you call it, it always returns the same address. That means you always get a single ring buffer. And this ring should be well known across the whole system because there are a lot of classes engaging in the processing. And for example, executor and awk, all the instances should see the same ring buffer. And how to do that? Since this ring buffer is unique and it will not be changed during the runtime. So we choose to add a static member field in the executor class and awk class. When we want to enable the ring buffer feature, we firstly initialize it with the get API, and then we assign the allocated address to the executor class and awk class. So, and we do this in the awk daemon init process. So after the initiation, every awk, no matter you want to instantiate a specific awk, it always knows the correct address for the ring buffer with this function. Okay, and that's the ring buffer part. And we take the Orchagent as the example to show how we use ring buffer to implement the multi-threading in the workflow. And we also found some similar pain points for other submodules. So finally, we use ring buffer and the multi-threading methods in both Orchagent and Syncd. And we choose to use the templated class to implement ring buffer so that every submodule can have a customized version of ring buffer. They can decide what data structure I want to store in this ring buffer. And that would introduce more flexibility. And with the template, we can not only change the ring entry type, but also the ring size. So that's very flexible. And we also do a lot of research on the ring entry data structure design. We have to decide what format of the data that we want to push into the ring. The goal is to choose a more general and flexible data structure so everything can be fit into the ring. And for example, this is the Orchagent workflow. To make the assistant thread work, we should know what this new thread wants to know. So firstly, it needs to know the data it needs to process. For example, it has to have the copy of entries. And it also needs the describing information of the function signatures to deal with the entries. That's all the information the new thread needs to know. And for the Syncd example, it's more complex because for the assistant thread, it's sometimes it needs to execute the functions like the first line. Sometimes it needs to execute functions like the second line. And those functions have different signatures. And to put those things into a ring buffer, you have to have a general format. And how to put these functions with different signatures into the same format and store it into the ring buffer, that's a point that we put much efforts on. And then we come up with the Lambda function solution. So this is the Lambda function, and this slide is a simple syntax overview of function object Lambda function. So Lambda function has another name, anonymous function. So it doesn't have a function name, but you can define the parameters there and return type and its function body. And we choose the format on the right here. It means we would copy every local variables the equal symbol means we would copy all the local variables, not defining the Lambda function, but used, maybe defined outside the scope, but used inside the Lambda function. The equal means we would implicitly copy the values into the Lambda function. And the example on the left is that a process get stats event function. It's originally a function with KCO as input and return type is size status t. But after I wrap it into a Lambda function body, it becomes a function object which has no parameter and returns the size status t. It's just a conversion. It does the same thing, but the format is different. The function type is different, but actually it does the same thing. And I just use Lambda function to convert the function signatures. And here, the goal is to store the Lambda functions inside the ring buffer instead of just data. And we can define, rename the function object as any task, then put the any task into the APIs I mentioned before. When the main thread do push ring buffer, it actually pushes the function object into the ring buffer. And when it does the pop ring buffer, it actually pops the function object. And we can also do the condition determination. If the ring buffer feature is enabled, okay, we call the ring buffer push. And if it's not enabled, we just execute the function object. Then the logic is the same as before the modification, because what passed in directly gets executed without the engagement of ring buffer. Okay, so I think the top benefit here is the small code change, because we only need to wrap the function with some brackets and yeah. And once the main thread wants to wrap up the workload and offload it, it just wraps the code snippets with some brackets, and everything is done. And you can see the comparison in the pictures. Yeah, just add a few lines. And some other small points here. Firstly, I think the important thing to accelerate the whole workflow is to avoid unnecessary data copy. So here are some small C++ tips. So the first thing is we would replace the copy assignment with the move assignment, so that we avoid a copy here. It would transfer the ownership of the data to the buffer tail. And the ring entry, after marked it with std move, this variable becomes undefined. You cannot use it anymore. And the data controlled by ring entry now becomes the data of buffer tail. And it's just a move. We avoid a data copy by using std move. And another thing is that since we push a Lambda function inside the ring buffer, the Lambda function is a temporary variable. So we could use the right reference of function, so another avoiding data copy here, because the reference would directly pass the temporary variable inside the function body and to process. Yes. And the third point is to copy pointer instead of copy value. So this is the original code snippet in the Orchagent. It would pop data from application database to the local variable entries, then push ring buffer the Lambda function here. But the Lambda function would by default copy the entries inside the Lambda body. And we change it to a pointer like this. We allocate a pointer to the DAC and pops the data into the pointer. So when the Lambda does the copy, it copies the pointer address instead of the whole data. And since the shared pointer in C++ would handle the lifetime of variables automatically, it would allocate memory space on heap when you make this declaration. And although even if we go out of these function scopes, the variable will still be alive until the last reference to the entries pointer gets consumed. So another avoid of data copy here. And now let's come to the performance potential part. With this optimization, we tested on Alibaba's ESR platform with 2 million routes, and we reached almost 12K routes per second. And we measure the push ring buffer function and the pop ring buffer function. The busy column means how many times it works during processing, and the idle time means the gap between each function call. So we calculate the performance by dividing the routes number by the total time and by the busy time. So by squeezing the idle time, I think the last column is the ideal performance we want to achieve with the final parameter tuning. Yeah, and that's like next step for our project is to like make the idle time less shorter and shorter in the future. Yeah. So that's all. Thank you. Any questions? Mm-hmm. Lock?
Because if it's one, if the processing time is the same, for example, you do have two threads, but you keep blocking on the lock. Right? The second question is, if you think maybe to, for example, instead of having one message, like I read X messages and then just push X messages into the read. One operation is the queue, right? Which is cheaper because it has protection and maybe system call, right?
So about the lock question, because the first thread, it would like only deal with the head pointer, and the second thread only deals with the tail pointer. They don't have shared.
But if you put one, let's say now you put one in the head, and then you get one from the tail, and then the tail keeps.
Oh, but after you push data to the head pointer, it increments by 1. So next time. It will not lock because if you add a lock there, you want to protect something. Then if you add lock here, what do you want to protect? Oh. Oh, but before you pop ring buffer, you would check whether there is data inside the ring buffer. Then it would compare whether tail and head are equal. If they are equal, that means empty, then it would not pop. So before it did any modification, it would check the tail and head, and to make sure there is data. Yeah. And before the main thread push data inside the ring buffer, it would also check the tail and head to make sure it's not full. And there is still some waiting time because when, for example, if the pops are very slow and although it pushes like 5 tasks in the ring, and let's assume the 6th task is very slow and the green workflow has already consumed all the 5 tasks, it still needs to wait. Yeah, so we need to like tune the parameter to determine the pop batch size and the pop frequency, things like that, to make sure there is no wait. Okay.
I was curious, what is the cause for the high return? Is just the difference between how fast it writes and how slow it reads? Like, what's the, why is it not?
So for the main thread, it pops data from the application database, and the data is like flushed by FPMSyncD. And the FPMSyncD, when it flushes to the application DB, it also needs time to like write, and write is very slow. Yeah.